welcome to another CosmoVerse seminar. Today we have the pleasure to host Glenn Starkman. Glenn is a distinguished professor at Case Western Reserve University. He got his PhD at Stanford University, followed by postdoctoral positions at the Institute for Advanced Study in Princeton and the Canadian Institute for Theoretical Astrophysics. He was also awarded with the status of fellow by the American Physical Society. And his research interests include searching for evidence of non-trivial topology of the universe in microwave background data. And today he's going to talk about the fact that the universe is not isotropic. Glenn, the floor is yours.
Thanks so much for Costas. So of course we know the universe is not isotropic because we look at and see all sorts of anisotropies. But I say this in the same sense that we say we live in an isotropic universe, that we don't live in an isotropic universe, namely that the universe is not statistically isotropic. So I want to tell you about lots of evidence that's been accumulating to this effect over the last decades, and why I think it's come together to the point where we should really take it seriously. And then maybe give you some hints of things that this might lead us to, and why this is very interesting to think about. So obviously, as usual, when we talk about our work, we're talking about work we've done with lots and lots of people, and I wanted to highlight some of them. I hope I got all the people I've published on this with in this list, and highlighting some of the people who do not yet have permanent jobs on the list. Most recently, Joanne Jones, who is a newly starting graduate student in astronomy at Chicago. But also you'll see other names here that you should look out for. We have a theoretical collaboration, or a collaboration of theorists working on these questions, looking at, it's called the Collaboration for Observations, Models, and Predictions of Anomalies in Cosmic Topology. And you see lots of the names here. I put all the senior people down below the line because they're already all settled, and the graduate students and postdocs above the line, so you can look out for them. And those of you heading off to Kyoto or Tokyo sometime soon for the Cosmo meetings can look in particular for Dayan and Javier, who will both be there, as well as Andrew Jaffe and I. All right, so it's been a really great run for the CMB, starting way back in the 1960s, before I suspect much of the audience was born, and when I was just toddling around, when with this telescope that just got rescued from the wrecking ball, Penzias and Wilson were able to make this incredible map of the cosmic microwave background. I just spent some time yesterday with some of our undergraduates, our great undergraduates here at Case Western Reserve University, telling them why this map is so interesting, because it doesn't really look like much of a map when you look at it. It's so homogeneous. And of course, there's been a huge amount of work over the intervening six decades to improve on this map, to see the small differences from place to place on the sky of the cosmic microwave background. I'll just point out the satellites that made as close as you can come to an all-sky map. COBE, which made this first map showing us the signal to noise, showing us significant fluctuations in the cosmic microwave background, not just the galaxy. And then, of course, the Wilkinson microwave anisotropy probe in the first decade of this millennium, which was able to make this gorgeous map. And most recently, the Planck satellite, which was able to make this even far more detailed map. And of course, many balloon and ground-based observations of the CMB in the meantime, as well as observations of polarization, not just temperature. But one of the things we're taught in cosmology kindergarten to do with this map is to expand it in a spherical harmonic expansion. So why do we do that? Well, it's because the standard model for those fluctuations teaches us the sky is statistically isotropic, and so these ALMs, these coefficients of the spherical harmonics, are independent Gaussian random variables all of the interesting information is contained in their variances, C sub L, which depend only on L and not on M because of the statistical isotropy. And the expectation value of any pair of them is 0, except for the same one, modulo the star there. And that is a fundamental tenet of how we go about thinking about the universe and analyzing the data in it, modulo small corrections that we are searching for non-Gaussianity that was there from inflation. Now, we're able to look for, so if all the interesting information is in these variances, we go and try to estimate them from our maps and construct angular power spectrum. Here's a relatively old one, but a nice one in which we see angular power spectra of temperature and E-mode polarization and cross between temperature and E-mode polarization. And I think the remarkable thing, I think you have to agree about these curves, is that we can do a 6 or 7 when we properly include curvature, parameter fit to far more than 7 independent points, right? So this is really a remarkable, astonishing experimental accomplishment that produces remarkable agreement with theory. And if that was the end of the story, I would stop right there, and it would be a very short talk, having nothing to do with the lack of statistical isotropy. But I think there's a but, and so this claim, this assertion that the sky is statistically isotropic, is really important for the whole data analysis, for how everything we do to think about the CMB and the universe. And the question is, shouldn't we check? And so, of course, the answer is yes, we should check. And I think what we discover is that there are troubles in our isotropical paradise. And I'll talk about a few of them, what gets called the low L, or really should be called the large angle problem, low L alignments, hemispheres, parity, etc. And I would like to convince you that the bottom line is that the universe is not actually statistically isotropic, and then leave you with some promises of topological musings. Okay, so let's come back to this first all-sky map. And the first hint that something was funny, I think, was the fact that the quadrupole of the angular temperature, angular power spectrum was low. Now, in fact, this isn't actually a correct hint, and we'll talk about that soon. But people noticed that, and were disturbed by it is the wrong word, because the excursion is not that big. There's a lot of cosmic variance shown here by this gray band, and so the quadrupole is low, but not not that much more anomalous than this point here, or this point here, or this point here, way at the first peak. And there are interesting stories to tell about those points as well. But I'll just say that low quadrupole was taken perhaps as a hint. The thing about it is, I don't think it should, you shouldn't really think, what's odd about that low quadrupole is not the lowness of the quadrupole. You really have to look at this in angular space. So not looking at the low quadrupole, but at what's really going on at large angles. And so if Kobe had flown maybe 10 years earlier or so, in the 70s, it would have done what an astronomer would have told it to do, and what people originally, I think, were thinking to do, which is measure the angular correlation function of the temperature on the sky. So take two directions on the sky, measure their temperatures, take the product, average over all such pairs of points that have the same angular separation. Now, of course, that has exactly the same information in it as the angular power spectrum, just differently organized. Of course, that's not that unusual. whenever we take a Fourier transform of data, we're just reorganizing our data. But sometimes when we reorganize the data through such transforms, we learn interesting things. So here is the a paper from the Kobe collaboration, in which finally, after 4 years, they present the 2-point correlation functions. Because of course, they took, they took their cue from the theorists who told them the interesting thing was the angular power spectrum. So that's what they told us about for the first 4 years. But finally, they did come out and publish their 4-year, their 2-point correlation functions from the 4-year anisotropies. And this is what they saw. And you can't tell yet that this is anomalous. People realized it was anomalous, and I'm not going to tell you yet how it's anomalous. I'll tell you that in a moment. But keep these maps in mind because people certainly noticed something odd about them. But it wasn't really until WMAP came back and measured the sky on these scales with much greater signal to noise, and pointed out in a statistically well-characterized way that there was something wrong. Okay? So what's going on? What's going on is if you look at these maps, you'll see that the angular correlation function is very small compared to from about 60 degrees or so up till nearly 180 degrees. Okay, so here it is in the 3-year WMAP data. We see that in all 3 of the bands that the WMAP team measured, the QV and WMAP bands, that there is a lack of angular correlation from about 60 or so degrees up to about 170 degrees. Now, when you exclude the part of the sky that includes the plane of the galaxy, that same thing is true. It's not true when you look at the maximum likelihood estimated CLs and use that, that formula that I showed before to turn that into an angular correlation function. It's still pretty small, pretty close to 0 compared to here is the theoretically expected angular correlation function. The blue band is kind of the 1 sigma error band around that, but you have to be very careful about doing a kind of chi-by-eye fit because the error bars are very correlated everywhere across this band. So the 2 things you should notice is first that these curves, none of these curves look like the theoretical curve. They don't lie well within the 1 sigma error band. But that's not actually what's weird about the observed curves. What's weird about them is that they hug 0 over most of the range from about 60 degrees up. And what's a little strange is that when you do the maximum likelihood estimate of the CLs, or when you take the independent linear combinations map and don't exclude the galaxy, those 2 agree, and you find a little bit more correlation. In other words, if you take the part of the sky that you don't trust, there seems to be correlation coming from that part of the sky, but not from the part of the sky outside of the galaxy. And indeed, if you go and check, what you'll find is, so if you take only points outside of some reasonable mask of the galaxy, you find very, very little angular correlation. George, you have a question?
Yeah, sorry. Yes, I mean, when you do the maximum likelihood, you can do the maximum likelihood on a cut sky. Okay, so you're not using the, galactic plane data.
Correct.
It's just a different estimator. That's all.
Absolutely.
Okay.
I'm not saying you did. You do.
All right.
Yes. Yep. You're right. Thanks. But what you find is that if you take the full sky, you have a little bit of correlation, still less than you would have expected, but all of it comes from pairs of points, at least one of which is inside the KQ75 mask. Okay, and and that much of the correlation, even at these very large angles, seems to be some sort of residual of that, in the sense that it's this bump at, this dip at 180 is going away as you exclude points in the galaxy. Okay. Thanks. So is that large angle anomaly significant? So WMAP, unlike COBE, tried to put a number on that, and it's been called ever since S1/2, because what they chose is the integral from 60 degrees up to 180 degrees, or in cos theta from -1 to half of C of theta squared d cos theta. And you can look at this in lots and lots of different early WMAP or all the WMAP maps, and what you find is that even though the expected theoretical value of that S1/2 is about 50,000 micro-K to the fourth, if you measure it on the full sky, you get something like 8 to 9,000, and if you measure it on the part of the sky outside of the galaxy, you get about 1,100 to 1,200, and that happens, randomly about 2 or 3 times per 10,000 random realizations of lambda CDM. Now, I think most of us wouldn't have been surprised if that was just some sort of systematic effect. If there was some problem with the instrument, something in the scan strategy, I don't know, and that when Planck came along, we found something, or Planck team found something completely different. But did this change in Planck? No, the same thing is still there on the sky, with the same values of S1/2. So, for example, you can see here in various methodologies of reconstructing the full sky, and then of looking at the part of the sky outside some similar mask, you come to similar numbers as WMAP, namely somewhere between 1,100 and 1,200. Okay, and that happens less than 0.1% of the time in random realizations of lambda CDM. Okay.
I think there's a question. Sorry.
Yes. Question.
Hi, Glenn. So my question is, for the curves you just showed on the last slide, are there uncertainties, error bars?
There are uncertainties that are small compared to the size of the problem. So, or if you like, there are the uncertainties are probably better characterized by the differences between these different maps than by the measurement error bar, the results of the measurement error bars on the data points. Okay, so most of the uncertainty has to do with foreground, treating the foregrounds.
Okay, thank you.
The maps are signal dominated. Okay,
yeah.
So the only residual uncertainty you have is how well you can eliminate the galactic foreground emissions.
Thanks for stating what I said, George. Thanks, that was well said.
I see. Thank you.
So somewhere around 0.03 to 0.1% of realizations of the concordance model of inflationary lambda CDM have so little cut sky large angle correlation. Okay, but most of those accomplish that in a different way than the sky does, because if you go back and look at the sky, only one of the low LC sub Ls is actually small, right? The quadrupole, and its p-value is about 0.1, so you get that low quadrupole about 10% of the time. And so what's actually happened is not that all these low LC sub Ls are small, which would of course give you a low S1/2. What's happening is that the contributions from the different CLs are canceling one another, so that to get S1/2 less than about 1,000 with requires correlating C2, 3, 4, and 5 to cancel out the contributions of C6 and above. And so, and you can kind of see that if you try to solve this problem by, for example, changing the power, the underlying power spectrum, or if you like, changing the theoretical angular power spectrum. Say we replaced all the theoretical CLs by their measured values up to L equals 20, and then we did random realizations of ALMs using those C sub Ls. It turns out cosmic variance would give us only about a 3% chance of recovering so little correlation in particular realization, because the low LC sub Ls have large cosmic variance, and so they would not cancel each other in the right way. And it turns out most of those would actually do it by lowering, most of those, 3% would do it by lowering many of the low LC sub Ls and giving you a poorer fit to the theory than is in the current data. So how do we explain the small s1/2? Didn't that go away? No. You can say, well, I never believe in a posteriori statistics, and that's fair. You can ask, well, wouldn't we have noticed all sorts of other weird things? And we'll all start to talk about that. It was certainly a reasonable initial reaction to this. I never believe anything less than 5 sigma. Well, that's particle physics. I've heard someone said to me 10 sigma. I don't know why 10 sigma. At some point in a theory where we can't do experiments in the laboratory, we have to have some criteria. I don't know what it should be, but at some point we have to start believing that there's something strange going on. Can inflation do that? Well, not easily, because if you could just change the angular power spectrum, inflation, you could do that. You could change the potential of the inflaton. But in this case, it seems that we need new physics that correlates C sub Ls. In other words, the expectation value of pairs of ALMs can't be proportional to delta L prime if you want the C sub Ls to get correlated. And that would mean you have a violation of statistical isotropy. Now, that's a strong statement. That's a strong claim from just one piece of evidence. And so I think we want to keep looking before we believe something so important about our universe. So if this is not a fluke, then probably it means that we're in the wrong, we're using the wrong basis if we want to preserve Gaussianity. So you can imagine, for example, that you cut off all correlations beyond some length scale. We call that a compact support basis. Turns out that doesn't work just doing that. What you get is you do in fact get a low angular correlation function, but you don't get a low dipole subtracted angular correlation function, which is what actually we are always plotting when we plot the angular correlation function. So not clear exactly whether that works. Okay, so is there anything else? And certainly pretty quickly after, especially after the WMAP data started to come out, people started to look at, in all sorts of ways, for departures from Gaussianity and statistical isotropy. And I've just told you one of them. So I'm going to tell you about a couple more that are somewhat representative of this large set. Many of these large set are probably tightly correlated with one another, but if I choose a few, I'm going to try to choose 3 that I've thought about that one would not necessarily think are correlated with one another, and then we'll check. Correlate with one another in lambda CDM. In other words, if they're weird, their weirdness is not a realization that has one particular anomaly would not be expected to have another anomaly. Okay, so and to do this, we're going to try to go beyond just the C sub Ls and talk first about alignments. And so if you look in the sky and you see the flight of birds being in some sort of pattern like this, you don't think it's random. You think that there is some organizing principle. And so the question is, do the ALMs have any sort of organizing principle that they're not supposed to have? So if there's violations of statistical isotropy, how is it organized? And when we set out to ask this question a long time ago, we got inspired by the dipole, because for the dipole, of course, you don't usually tell people what A11, A10, and A1-1 are. You tell them what the direction of a dipole is and its magnitude. And you do that because maybe because we understand intrinsically what vectors are. We have a gut feeling for them. So if I tell you that its direction and its magnitude, you have a physical sense of what it means. And indeed that vector transforms under rotations like a vector, and its amplitude like a scalar. So we can understand what that means. Well, is there something comparable for L's greater than 1? And the answer is yes. You can represent, say, a particular multipole L in terms of a product of L dipoles. Now, of course, when you take that product of L dipoles, you won't just get the angular momentum L piece, you'll get all sorts of other pieces, but it's straightforward to subtract all those other combinations out. And so you can represent the information in the 2L plus 1 ALMs of a given L by a single scalar and L unit vectors. Okay? And we call those multipole vectors. We didn't invent them, much to our chagrin or surprise or delight. It turns out someone else did, or at least someone else that you know used them. Maxwell used them in this relatively well-known book called A Treatise on Electricity and Magnetism. And that is how Maxwell thought of data on a sphere. In terms of directional derivatives of 1 over r, and these turn out to be exactly the same multiple vectors. Okay? And that way of representing data on the sphere hasn't gone away. There are corners of physics in which that is how one represents data on a sphere, but it hasn't been a dominant way in particle physics or cosmology. Okay, so it was probably unfamiliar to most of you, and it was unfamiliar certainly to us. Okay. So notice that the quadrupole has 2 vectors associated with it. So you can think of the quadrupole as defining a plane. The octupole has 3 vectors, so you can think of it as defining 3 planes from every pair of them, which suggests defining the normal vectors to the plane, and you can include the magnitude of the area in that or not, but basically the cross products of pairs of those vectors. And those will carry not all, but much of the information in the multiples. So let me just show you how they're distributed on the sky in this very old plot. And we vowed at the time to keep showing it this way, so no one thought we were massaging the data with all the things on here that probably turned out to be irrelevant. Okay. So here we go. There's the quadrupole down here, this dark gray, and it's all, those are headless vectors because I don't know what sign to assign to the scalar. So depending what sign I assign to the scalar, I can either put the quadrupole vector, area vector in the south or the north. I'm going to focus on the south just because it turns out that in the north, they kind of wrap around the sky. So you see like one of the octupole vectors up here. So let's just look down here in the south. Here's the quadrupole vector. And here are the 3 octupole vectors. Okay, so you see that they are all in one small part of the sky, whereas they could have been anywhere in this southern hemisphere. They turn, so right there they are clustered together. They weren't supposed to be clustered together. In particular, the quadrupole and octupole vectors are completely independent in a statistically isotropic sky. And the octupole vectors are not actually completely independent, but they're supposed to be much more widely distributed than that. So this clustering in one small area is unusual. It's actually even a little worse than that because you'll notice that the quadrupole is sitting pretty much at the center of the 3 octupole vectors. And we'll talk about that in a minute. Okay. And this if you've heard of something called the axis of evil, that's just a different way of thinking about these things. The quadrupole axis is exactly this quadrupole area vector, and the octupole axis is the mean of these 3 octupole vectors, and the axis of evil is the observation that those 2 things are aligned. And actually, what's in particularly strange is that they become more aligned when you remember that you're supposed to subtract the Doppler contribution to the quadrupole. Now, there are other things here, like you'll notice that they seem to sit quite near the ecliptic plane. They also sit quite near the dipole. Here's the dipole right here. They also sit right near the equinox. All things that we wondered whether, in WMAP, whether these had to do with systematic effects from the satellite observational program. Okay, the supergalactic plane. So let me focus on this fact that the quadrupole and octupole planes are aligned with one another with a p-value that, depending on exactly what map you look at, is somewhere between 0.1 and 0.6%. Okay. Again, not enough on its own to make you say, oh, well, let me forget about statistical isotropy. You might worry that this is coming somehow from the solar system. As far as we can tell, it isn't. The fact that Planck and WMAP saw it suggests it's not really systematics in the observational program or in the telescope observation. It doesn't appear to be dust in the solar system, et cetera, et cetera. So this does appear to be on the cosmological sky. Now, there are other things. It's been goes by various names and various statistics. Some people will call it power asymmetry. Some people will call it dipole modulation. We've tended to describe it in terms of something we call low northern variance. And you can kind of, it was really Bennett et al., and then who saw it first, I think, and Erickson et al., who maybe characterized it first. And you kind of can see it for yourself that if you look at this map, this part of the map up here seems to be quiet compared to sort of this part of the map down here to be lower variance. There've been a number of ways of comparing that. So here's Erickson, Hansen, Bundy, Gorski, and Lilje in 2004, showing us that the binned angular power spectrum over the unmasked sky, here's dashed, here. And then if we look at the northern hemisphere, that's the solid line down here, and the southern hemisphere, that's the dotted line. And you notice that the dotted line is pretty consistently above the solid line. Here's another way of looking at it, just looking at the variance over the north and the variance over the south. And here's the probability distribution that you'd expect for the temperature variance in a hemisphere. Here it is, and here's the south sitting at pretty much the most likely value of that variance, and here's the north sitting way down in the tail with no variance, and you could indeed describe that as dipole modulation, although I would have thought that if you were thinking of it as dipole modulation, you would have ended up with a high south and a low north, and so we've tended to call it low northern variance. Okay. And you might ask, well, is it OIC?
Yeah, there's a question.
Yeah, you how?
Yeah, it could be say you're also planning to explain this, but the question I got is this way of dividing between north and south maximizing this variance
Great.
difference?
Thanks, Seth. Yeah, I think I do think you asked that question of one of the other students at one of the recent talks recently. But let me answer that for the whole group.
Okay. Thank you.
So because it's a great question, it's a good, really great question, and the answer is no, it's not optimizing that. And so there's a little bit of a look elsewhere penalty if you do optimize it, which you should pay. But this is actually ecliptic north and south, which is not quite optimized. So you should probably pay a little bit less of a look elsewhere penalty. Yeah, so exactly what the p-value is if you optimize turns out to be similar, but good question. Okay. So Here's another odd thing, closely related. Again, p-value like this, you do not throw out the entire idea of statistical isotropy. You might start to get concerned. Okay. Parity. Okay, so if you look at the C sub L's at low L and start to look at them, you'll notice that if I have here L equals 2, I go up to L equals 3, L equals 4, I go up to L equals 5, L equals 6, I go up to L equals 7, 8 go up to 9, 10 go up to 11, 12 go up to 13, 14 go up to 15, 16 go up to 17, 18 go up to 19, 20, oops, I go down to 21. So there's this kind of consistent pattern of the odd modes being higher than the previous even mode. Okay. And people have tried to put put statistics on that. If you just guessed at the statistic, you would say, oh, well, what's the chance of that? Well, I had, let's see, how many pairs here? 1, 2, 3, 4, 5, 6, 7, 8, 9 pairs. So 1 over 2 to the 9th, but I would have noticed if it was even then down to odd. So that's 1 over 2 to the 8th, maybe 1 over 2 to the 7th. And so I would have imagined some p-value around 0.4 to 1%. People wrote down actually wrote down a different statistic to just compare the overall power in the even and odd modes. That gave a p-value more like of a couple of percent. Again, another anomaly that is strange, not enough on its own to throw out statistical isotropy. There are lots of other things. You go and look at all of these other funny values of C sub L, and strangely, what you discover is that they exist only in the ecliptic polar regions of the sky and not in the ecliptic planar regions of the sky. Okay. You look at BIPOSH coefficients, which is a way of describing, so remember that what I called low northern variance has also been described as dipole modulation. In other words, that over the sky, the power is modulated with a dipolar fashion, and you can describe that in terms of something called bipolar spherical harmonic coefficients, and the L equals 1 bipolar spherical harmonic coefficient talks about dipole modulation. You can also have quadrupole and octupole, etc. modulation described by higher and higher capital L BIPOSH coefficients, and here those are as plotted by the Planck collaboration in 2014. And what was reported is how anomalous the L equals 1 BIPOSH is, nearly 4 sigma anomalous, p-value of 0.02%. One has a strong sense that that's closely connected, as I said, to low northern variance. But none of the others rise to the 3 sigma level. However, notice that if you draw a line here around 0, through 0 from side to side, that a surprising fraction of these are below the line. In other words, these do not look to be Gaussian distributed at all. And in fact, L greater than or equal to is also nearly about 4 sigma anomalous in any reasonable test of whether these are actually whether these statistics are actually distributed with the statistical distribution that we would expect in lambda CDM. Instead, they seem to have a lot of excursions to small values. Okay. So with so many anomalies, what should we do? Well, one of the things we should do is we should put them all in one place for people to judge and to evaluate. And Planck wrote a couple of very good reports each time, in each of their major data releases about isotropy and statistic. And we're in the process now, a few years later, of trying to put together a review of the approximately 2,000 papers that have been written in various ways about this subject. I want to tell you about one of those papers, which looks at the question of, okay, there's all these anomalies, but is the combined likelihood of them approximately the minimum of the worst of them, or is it the product of all of their probabilities? And because those are radically different numbers, as I said, the worst of them is, has a p-value of, let's say, 1 to 2 times 10 to the minus 4. But there are many of them, over a dozen. And 1 to 2 times 10 to the minus 4 raised to the, to the 12th power is a very, very small number, radically different than 10 to the minus 4. So how much evidence is there actually that the universe is not statistically isotropic? For this first analysis, we just picked out 4 representative anomaly statistics. What do I mean by representative? Do I mean that we picked the worst ones? No. For example, you won't see that L equals 1 biposh in there, nor the L greater than equal to 2 biposh. We picked 4 that seem to us reasonably likely to not be correlated, because there's a lot of others that are correlated, that are likely to be correlated. Adding them in will only make the collection more unlikely. But what is the evidence of just this handful present? So the first, you want to know, are these correlated in lambda CDM? And we're not the first ones to ask that question. And of course, what does it mean to be correlated in lambda CDM? It means to compare the different, to look at the different maps that have tried to, in which one can try to measure these. And we use, these 4 Planck 2018 maps. Something similar was done by Muir, Adhikari, and Hutterer. What they did, though, is they looked at the peak of the distributions. Okay, so they asked, at the peak, at the peak of these distributions, are they correlated? And they found some correlations, but not strong ones. But that's not really the question we're interested in, or most interested in. I think what we're most interested in is, in the tails of these distributions, out at, one part, a p-value of 10 to the minus 3 or 10 to the minus 4, if you have one of these anomalies, do you also get another? And so, the combined p-value is just the minimum of the two. So here we are looking at about 10 to the 8th noise-free realizations of CMB in best fit lambda CDM. You'd like to go way beyond, much beyond this, where you do chains and not just best fit, et cetera, et cetera. And what you see is that here we have a statistic S1/2 that characterizes the lack of large angle correlation, a statistic that includes that characterizes alignment, one that characterizes hemispherical asymmetry, and one that characterizes parity. And you find that there's only, so these numbers here tell you pairwise, if they're 1, then these are completely uncorrelated. If this number in blue is less than 1, then they're anti-correlated. And if it's greater than 1, then they're correlated. And you see here that the one pair that is consistently correlated across all the maps is the lack of large angle correlation, S1/2, and the hemispherical, the low northern variance. Okay, so now they're correlated. It's still true that the product of the two of them, here's, for example, in the commander map, this one, S1/2 has a p-value of 0.1%, and the low northern variance of 0.3%. Okay, and the product of them has a p-value of about 0.01%. Okay, which is less than the product of those two, but still, sorry, greater than the product of those two, but still, a factor of 10 less than either of them. And that's kind of typical across either of them. And we can do the same for triplet correlations, and you see that there's no further triplet correlations of any significance. And so if you look at those four anomaly statistics, what you find is that 7 is a bit of an outlier. About 2 times 10 to the minus 7 is the, so out of 10 to the 8 realizations. There were 18 that had all 4 anomalies. Commander had 3, SMICA had 1, and NILC had none. Okay? So correlation factors of about 50. So are they correlated in their tails? Weakly, but only weakly. And so if you take these 4 statistics, you would conclude that statistical isotropy is falsified at greater than 5 sigma in the CMB TT correlations. In other words, that the universe is not statistically isotropic. Now, you may worry, and you know, at least two points have been raised for this, you know, about this. One is perhaps you should take a strongly Bayesian viewpoint and say that you can't believe data without a model. So if you have anomalies, unless you have an alternative model, you can't falsify the first model. I don't think that's how physics actually works, and I'm happy to provide lots of counterexamples. It's a viewpoint that I don't share. What about look elsewhere penalties? In other words, can't you always find anomalous statistics? And I think there's a number of answers to that. One is, yeah, you can always find anomalous statistics. But what happens when pretty much every statistic you try off the bat is anomalous, which is approximately what happened in this looking at the low L data. Not every single one, but even ones that were reported as non-anomalous, like the L greater than equal to 2 biposhes, if you go back and look at them, aren't as non-anomalous as I think was thought. And certainly I've had this conversation with the person who looked at the biposhes, and he seems to agree that yes, those just weren't as anomalous as the individually as the L greater than 1. Are there a whole bunch of other statistics that are out there and people weren't reporting them? And so you should worry and multiply by some factor. Well, certainly we can devise lots of statistics, but it's unlikely that we can devise enough statistics that were looked at and weren't reported to make up for 5.5 sigma significance. Okay, and that's one of the points of these very strong criteria like 5 sigma. We don't really think that the reason you need 5 sigma is because we're only going to get concerned when we have, you know, less than 1 in 10 million chance that the data disagrees with the model. What we really are worried about is some combination of statistical fluctuations and our propensity to see patterns when there are none. When they're just there by chance. And so it's one of the reasons why we use 5 sigma is to protect ourselves against look elsewhere penalties. And we have, and there's a lot of evidence against statistical isotropy. And I know that not everyone's going to agree with me, but I think that you have to, at this point, start taking it very seriously, the possibility that the universe is just not statistically isotropic. Now, if that was the end, it would be kind of boring because, you know, what would we do in a universe like that? We would just sit here and debate whether it's statistically isotropic or not. And the data would, you know, we would have this data, and we could have beers, and, you know, and half of us would yell at the other half about whether it was statistically isotropic or not. But there's at least 3 things we can do when they're related. The best one would be to find a fundamental physics model and make testable predictions. And I'll give you a little bit of a hint of that as I try to rush through the rest of the talk. The second thing, and it's very closely connected to the third thing, is to make reasonable phenomenological extrapolations from what we see and test them. And the third would be to continue to test the fluke hypothesis, the idea that this is just statistical fluctuations in lambda CDM. Okay, so what does that mean? It means assume lambda CDM is correct and predict how measuring those anomalies affects predictions for other observables, and then test that. I warn you that this is I think, a fundamentally frequentist approach, but there you have it. What does phenomenological extrapolations means? It means assume that a given anomaly is physical and guess what that implies for other observables without a theory. okay? And we'll try to do a little bit of that, okay? So, and those two things really go hand in hand. So for example, think about low northern variance in temperature and ask, what does it mean for E-mode polarization? Okay, so here's the low northern variance in temperature, and you say to yourself, you have low variance in temperature over the large portion of the sky. That's due to underlying low variance in the curvature fluctuations, presumably. The E-mode polarization comes from those same fluctuations, so it should have low variance, right? Why don't we look at those? After all, T and E are correlated. And so you make some constrained realizations in which you have low variance in the north and T, and you ask what it does do to E, and you discover that it does almost nothing because they're weakly correlated, and it just doesn't work to lower the variance in E. Okay, so here you see the small shift due to the fact that you have low T. Okay. So you get a small reduction in the polarization variance, approximately equal in the north and south. Okay. So the phenomenology, if you want to test that guess, you would look for reduced variance in the northern ecliptic E. Here is what you would expect, say from the full ecliptic north or Atacama ecliptic north. And if you had the kind of 10% reduction, 10% suppression in variance that you got in T, go 10% down. Let me go back. It's easier to see here. Go 10% down from 12.6. So subtract 1.2, and you're whether you have all of the north or just what you can see from Atacama, the Atacama Desert, you are way off the chart, and you will have an extremely low p-value. So it's very unlikely that you would get comparable low northern E variance. Okay. Similarly, you might ask about angular correlation in polarization, given the lack of large angle correlation in T. Same kind of thing. You expect what does it do for Q, U, and E? And the answer is, first looked at by Dvorkin, Peres, and Hu. The answer is not a lot. This is from a paper by Yoho et al. You see that you don't get zero correlation above 60 degrees, like you might have thought you do. And then, people have, so here's what you predict, and here is what one observes. Okay, and one can ask how reliable is the low L Planck E mode or the low L Planck E mode ALMs. How well can we actually measure EE at separations of 60 to 180 degrees? But to the extent one trusts what we see, here's this paper by Giocetta et al., and you see a very low northern E, unexpected in lambda CDM. Okay. Now, there's important consequences to this. One is that a broken symmetry offers no protection. Symmetries protect us from all sorts of things. And so all of the off-diagonal correlations in temperature and E-mode polarization in B and cross-correlations between T and B and E and B, those are all not due to parity invariance. They're due to rotational invariance, statistical isotropy for the most part. So if you break statistical isotropy, the expectation value, the general correlation matrix between ALMs of T, E, and B and ALMs of T, E, and B is pretty much non-zero. And you can go to a paper by Amir Hossein Samandar and the rest of the compact correlation to look at that, at some of the consequences of that. And we're busy writing a much more complete paper about that. Another thing is anisotropy is not non-Gaussianity, so statistical, but most of the tests of non-Gaussianity assume statistical isotropy. And so if you don't have statistical isotropy, you have to be very careful about your measures of non-Gaussianity. And I'm going to kind of skip over that because I want to get to something else. But I think that's an important thing to be thinking about as we move forward and into more and more better and better tests of non-Gaussianity, how are they affected by the fact that we live in either a non-isotropic universe or a very non-isotropic realization of an isotropic universe. The best thing, of course, would be new models. And here is the list of new models that we know are able to explain the observed anomalies. It's empty. We don't know of any model, I think, that explains all these anomalies, because what you have to do is you have to break statistical isotropy and affect scales that were causally disconnected until recently. You can't, it's very hard to do from foregrounds. We don't seem to be doing it. Systematics don't seem to do it. It's hard to do it from propagation of photons along lines of sight. However, there are fundamental physics phenomena that break isotropy and are already in our theory, and at least one of them that is fully within GR is the possibility of non-trivial cosmic topology. Okay? So we spend a lot of time thinking about the possible curvature of the universe and less thinking about topology. But you can see very quickly, so here is a flat two-dimensional space, and you can think of it as not having boundaries, and then it would be what we call the covering space of two-dimensional Euclidean space. But if you cut a rectangle out of it, or actually any parallelogram, and identify the opposite sides, you still have a flat space, but it has non-trivial topology. It has the topology of the two torus. Same thing happens in three dimensions. We can have a three torus. The simplest version would be to take infinite space and cut a cube out of it and identify all the opposite faces of the cube. And you can see that there are special directions in this space, namely the directions that match the directions toward the face. Now, it turns out that there's a lot more things you can do in Euclidean three dimensions. In fact, it turns out that there are 18 different topologies of Euclidean three dimensions, each of them with up to 6 real parameters. So there's a lot to explore. Same thing works in S3. And even if we know that the curvature of the universe is small, we don't know that it's zero. So we have to ask about spherical space. Yes, there's a countable infinity of classifiable topologies of spherical space, no real parameters except the curvature. The same thing happens in hyperbolic space. Much worse, there's a countable infinity of topologies, and they're not even classifiable. Okay. So a lot of work has already been done looking for cosmic topology. We know certain important things. We know that the shortest distance around the universe through us is greater than 98.5% of the diameter of the last scattering surface. But it turns out that that still leaves an awful lot of parameter space for non-trivial cosmic topology, and even non-trivial cosmic topology in which the universe is small enough to measurably affect the cosmic microwave background. And so, we've started to go back and calculate the correlation matrix for ALMs in these topologies, not just for temperature, but also for polarization. And there is what will be a large program necessary to go back and look at Planck data, hopefully at Lightbird data, hopefully in the future at 3D data where the signal should actually be cleaner, and look for evidence of non-trivial topology that perhaps explains the observed statistical anisotropy of the universe. So I would say that the CMB is not the realization of a Gaussian random statistically isotropic field. That would be the most reasonable conclusion. Or it is a very weird, incredibly unlikely realization of a Gaussian random statistically isotropic field, far weirder than I'm willing to accept is the explanation for what we see. So there are no proven models so far. It does not appear to be systematics or foreground. There's a potential cosmological model, namely that the universe has non-trivial topology. But whatever you believe, the cosmic orchestra may be playing the Lambda CDM symphony, but somebody seems to have given the bass and the tuba and maybe the cello and the viola the wrong score. And they tried hard to keep it quiet, and they failed, and we need to find an explanation. Thank you.
Thank you very much, Glenn, for a nice talk. Are there any questions?
Hi, Shaheen, go ahead.
So the question is whether we can see something similar for breakdown of isotropy in low redshift cosmology, for example.
Right. That's a great question, and one that you can, I think, only really answer in a particular model. Of course, we can go look for it, but a model will give us indications of that. So, if cosmic topology is the explanation for what we're seeing in the CMB, then what cosmic topology does, is two things. First of all, immediately it discretizes the eigenmodes of the Laplacian, and if those are, as in our conventional theory, if the amplitudes of those are the correct random variables, Gaussian random variables, in which to explain the observed fluctuations in the universe, then all of a sudden the spectrum of eigenmodes has been discretized, and you can look for the discretization of that spectrum. So, for example, it would mean in 3D, if we're in Euclidean space, that not all Fourier modes are actually are excited. Only certain Fourier modes are excited, which is what we know goes on in a periodic box. And of course, the bigger the box, the closer those modes are, the wave vectors of those modes are, and the harder it is to tell that you've been discretized. And so when the box gets bigger than about 1.2 times the diameter of the last scattering surface, it gets very hard in the CMB, and maybe you can still see it in 3D data that's of high signal to noise. We don't know. As you look at the other topologies, so they do something additional. So, for example, the simplest next topology in 3D is to imagine when you identify two of the faces of the cube that you would do to create a periodic universe, normally a 3 torus. Turn one pair. Say you turn it by 90 degrees. And what that would mean, let me do it in the z direction, that what that would mean is that four different Fourier modes that are related by a rotation by 90 degrees would have correlated amplitudes. In fact, their amplitudes would have the same magnitude and have a phase that is calculable depending on where you are in the universe. So notice I said where you are in the universe, which means that you, even though the background geometry is homogeneous, you spontaneously break translation invariance or homogeneity. What it really means is how far you are away from the axis of rotation of that topology matters. So can you see that in low Z 3D data? We don't know yet. We're busy trying to calculate that. We're cautiously optimistic, but maybe we're foolishly optimistic. I hope to tell you the answer to that sometime in the next 1 to 6 months.
Great. Leandros?
Yes. Hi, Glenn. Thanks for the interesting talk. I'd like to somehow expand a little bit more on your point of the look elsewhere effect.
Sure.
And try to quantify a little bit better the number of statistics that are not anomalous. For example, one can ask the following question: how many pairs of L's, of multiples, are not aligned? For example, you can take the first L equal to 1 to 10 and ask the question, what is the number of pairs of L's which are not aligned? And then get an idea of how probable is it. Has anybody looked at this to see how many pairs of L's are not aligned?
Okay, so Anders, let me say two things. First, I disagree with you that that's the right question to ask, but I'll come back to your question in a sec. And why do I disagree with that? That's the right question to ask. If I wanted to take a picture of this room, okay, that I'm sitting in, or probably the one that you're sitting in, and asked, are there any meaningful physically correlations of the pixels as I look around this room? Or is the patterns I'm seeing just random? I wouldn't take all possible pairs of pixels and ask if they're correlated and conclude, no, they're not, because there's huge numbers of pairs of pixels, way more pixels that are uncorrelated than pixels that are correlated. When actually I know that I see two whiteboards and a chair and a hat and books. And so I don't think you're asking the right question. I don't think it matters very much when we start asking this question, whether L equals 2 is correlated with L equals 753, for example. But what we do know is that when this all started, of people doing this, several of us were looking at more than just L equals 2 and 3 correlation. And the answer is, so for example, Hutterer, Copey, Schwartz, and I looked at L equals 2 to 8, and we found all sorts of weird things, more weird things than there should have been. By weird things, I mean pairs of multiples that were either too correlated or too aligned or too unaligned between 2 and 8. And we said to each other, okay, and you try to write down a statistic that describes that collection of statistics, and you get a statistic, and and you find it has a very low p-value. And you realize that telling that story is very, very difficult because it sounds like tea leaf reading. It sounds like looking up in the sky and looking at sheep. And so we said, okay, it's true that there's a lot more of these. We're going to confine ourselves to L equals 2 and 3. Now, Land and Magesiu also did some of this, and they found stuff all the way up to, if I remember, L equals 50. And if you look at those bipolar spherical harmonics that I showed you, right? Remember the L equals 1 was almost 4 sigma anomalous, but there were many, from capital L, which means the difference between L's, between ALM, the L's of ALMs. There were many up to L's of like 25 or 30 that deviated significantly from the distribution of them deviated significantly from what you would have predicted in lambda CDM. In other words, there were anomalous anti-correlations stretching across a wide range of delta L's. Okay, so I think the answer is yes. There are many correlations. Figuring out exactly which pair I'm supposed to look at is hard, and so that's not what people didn't look at all pairs, nor do I think they should have. But there's evidence that there are correlations, not just at delta L equals 1, but across many delta L's.
Yeah, thanks for the answer. The question is not to have some anomaly between two L's, but to have the same kind of anomaly. So you want to fix the statistic. For example, you can ask what is the alignment which is similar to the one L2 and 3, and then ask if the same effect happens for any other pair. If you choose another pair and then you choose another statistic, of course, you can find some statistics for any pair which is anomalous. I agree with that.
That's not what people did.
Have the same statistic.
You could, but that's not what people did. So
Okay.
it's true. There are many things you could do that would be foolish to do, but people didn't do those foolish things. They did simple things, for example, they calculated the capital L equals 1 BIPOSH and the capital L equals 2, 3, 4, etc. They BIPOSH, or they calculated what we did is calculated the alignments of the planes of the multipoles, or they calculated the alignments between the orientation axes of the axes that maximize the angular momentum dispersion of that multipole. So that they took simple single statistics and asked, do these align between, do these correlate between different multiples? And the answer was a surprising number of them did. And that's, I think the BIPOSHs are one comprehensive way, not the only, of looking at that, better than what we were doing in terms of the comprehensiveness. And so I think it's more interesting than what we were doing in terms of alignments of area vectors of multiples, and probably better than what Land and Magesiu were doing in terms of alignments of angular momentum dispersion maximization axes. And you see signals. There are other replacements for bipostures that no one has calculated. Maybe they'll be anomalous, maybe not. But you're exactly right. You shouldn't take every possible correlation of every pair. You should take simple ones, and that's exactly what people did. And most of them are anomalous. So, or
Okay.
unreasonable numbers of them are anomalous.
Okay, thank you.
Thanks.
Laura?
Hi, thank you for the very interesting talk. I have a question about the first part of your talk when you talked about the correlation function and compared it to lambda CDM simulations that are isotropic. And people are always worried about the low correlation function. I think at angles larger than 60 degrees, but in the plots you showed, there's also a deviation at smaller angles. If you look at like 20 degrees, for example.
Right. So if you look down
Mhm.
here, right, what you see is that below, below 60 degrees or below 50 degrees, the angular correlate, there's lower angular correlation on the sky than there is in the theory, right? That's what you're saying. That
Exactly,
is almost entirely low quadrupole. And that's why this is such a, it's very bad to do chi by eye from this graph because the points along the line are highly correlated. That's the advantage of C sub Ls, right? In lambda CDM, all the C sub Ls are independent, and so you can look at any pair and say, oh, that one deviates, right? But here, the fact that this is low and the fact that this is low are not independent, and the fact that this is low because in lambda CDM, right? Lambda CDM says the independent things are C2 and C3 and C4, et cetera. And so having a low C2 drives many, a whole set of these down, lower.
Thank you.
So Yuhao?
Thanks for the very nice talk. I still learn a lot more on this topic.
Thanks, Yuhao.
So first, as an experimentalist, so I would think it's natural to see further anomalies or like a disagreement between theory and data at some point if the data keeps improving. Because in that way, and then it means probably we're not going to have a perfect theory, but we can always improve upon the theory. And then say if taking this perspective, do you think there is any direction, specific direction in improving the measurements to better at least highlight the say disagreement between theory and the data?
So I think there's two questions. There's two elements of this. As George said earlier, the temperature data at low L is signal to noise dominated. So low L signals from temperature are probably not going to improve unless there's some fundamental improvement in our ability to confidently remove foregrounds. So maybe foreground removal gets better, but absent that, it's not going, the temperature data I don't think is going to fundamentally improve. What should improve is low L E mode polarization data, both in the sense of better signal to noise and or higher confidence in the low L multiples. Better measurement of tau turns out to probably be relevant, of the optical depth. So from a data improvement point of view, better measurements of polarization, especially at low L, would seem to be valuable, both from the point of view of improving the measurements of being, basically from the point of view of being able to test for these other anomalies, that or of similar anomalies, and of being able to test models. So, for example, cosmic topology will make predictions about correlations between T, E, and B that could be tested with with more and better E-mode polarization data. And then, so I think those are probably the main data avenues for improvement in terms of CMB. Yeah. There's a possibility that high L CMB polarization is also relevant. It's not, I don't think the theoretical understanding of that is yet firm. So if one can, it may be that one can use existing or future E-mode, polarization data at higher L as well.
Thank you.
Great. There are two more questions, and then let's wrap it up. Andrew?
Hi there. Hi, Glenn. You mentioned the cosmic topology as a possible explanation. There's a different mechanism that Marina Cortese and I worked on a decade ago or so, which I feel might be relevant, which is the possibility of having a large-scale perturbation running right across the universe. This was mentioned first by Adrian Erichek and collaborators. What Marina and I did was point out that if the universe is open, and here we mean really very marginally open, there's a particular class of perturbation modes known as supercurvature modes, and that open inflation models make this rather intriguing prediction that a single one of these modes is excited and can potentially be excited with large amplitude, giving rise to a gradient across the universe. When we looked at this a decade ago, it seemed very, very hard to make it work, but it certainly generates statistical anisotropy at some level. It seemed very hard to make it work, but we also found it very hard to be absolutely sure that it didn't work. And then we didn't really look into any more detail. Has there been any further work or ideas that show this is definitely not a good thing? Or should people be more?
So let me tell you why. I think it's an interesting observation, right? And that in fact the other place, a way to say it is that the other place you could get large scale, isotropy violation is from low L modes of something, right? Now it could be just low L modes of the the inflaton in or whatever scalars are responsible for all the other fluctuations. It could be organized structures like domain walls out there of some fields. Here is the thing that I think makes it a little difficult, maybe not impossible, is that we see statistical isotropy violation that correlates L's that are, that's several different separations of L's, okay? And so just a gradient, for example, just a gradient is not going to do this, right? And so now, so is there some superposition of super curvature modes that could, or low curvature, or large modes, super horizon modes in a low curvature, a low curvature universe that could do this? Maybe. Modes of high, unexpectedly high amplitude at large scales, you say, well, that's unreasonable, but no, it's not necessarily unreasonable because we don't understand the power spectrum on the scale of the curvature, if we see curvature. And so it's not completely unreasonable that there are large fluctuations just sitting out there that aren't topological in nature, but are just fluctuations on the scale of the curvature, right? And I wouldn't say that that's an impossible explanation. I'd say it's a potential explanation. We would have, the question is, can we infer what those modes are, right? And I think it's worth doing that work to ask that question.
Okay, great, thanks.
Thanks for bringing that up. Thanks for bringing that up, Andrew.
Thank you both. And the last one, Thomas. We can't hear you. Can you hear him, Glenn?
I can hear you, but I can't hear him.
Yeah, me neither. And it seems that his microphone is on, so I don't know.
Do you want to type something into the chat?
We can see you, but we cannot hear you, Thomas.
Sorry.
Oh, okay. No, it works. Now it works. Go ahead.
You hear me?
Yeah.
Okay. Yeah, well, I was thanking you for your talk, and I like your picture about the symphony.
Thanks,
And
Thomas.
I would like to ask you whether it could be Luigi Bianchi playing the tuba.
So that's a great question. The challenge of the challenge of anisotropic geometry models is that there's a quadrupole that we see, and that quadrupole is small. And so, for example, I've been thinking about it less in terms of Bianchi models and in terms of Thurston geometries, which are related. So you can show that and we have a paper out, that the equivalent of omega k in any anisotropic geometry has to be less than about 10 to the minus 5. Okay, and that's because the anisotropic expansion takes an isotropic CMB on the last scattering surface and lets the observer see a quadrupole and higher multiples. Okay, and perhaps higher multiples. And so it's hard to get much anisotropy in the geometry. So there are limits on Bianchi models. There are limits on Thurston geometries. And the other thing about them is, again, coming back to this idea of what bipolar spherical harmonic coefficients do we see? It's not just L equals 1. We see, so we see correlations across several L's that differ by a few. And so you have to have complicated geometries, I think, in order to induce those correlations. And I don't think, I think the Bianchi models and the Thurston geometries are going to prove to be too simple in their anisotropy to cause the correlations that we see. And I think that's why topology is more promising than geometry, because topology, I mean, take a cube, it has much more than a cube has a quadrupole, but it also has, L equals 4 and L equals 6. Put a twist in it, and you get L equals 1 if you don't sit on the axis, and L equals 3, and so immediately you get modulation of a wide variety of L's, of delta L's, that I don't think are going to happen easily in the non-FRW geometries.
Thank you.
So, yeah, thank you, everyone.